So the third part is about fakir drops. So fakir drops were discovered very long ago. Actually, when we look at the natural history of Pliny, 2,000 years ago, we find that drops on plants can be very special, and he says that these plants themselves are very special, and so he had the idea that very special solids can generate very high contact angles. But they were rediscovered in the late 90s, in particular by the Kao Corporation. Remember this picture, this is a flat wax. You keep the wax constant, the chemistry constant, and you make it very rough. The scale is 100 micrometers here, and so these bumps are decorated with smaller bumps of size 10 micrometers, which themselves are decorated by smaller bumps of 1 micrometer. It's a fractal surface. You take the same water, you deposit this water on this solid, and you observe this magnificent pearl of liquid, which made the cover of the journal Langmuir in 1996. And I think this cover attracted the eye of many researchers, including myself, I must say. When I saw this beautiful picture, I thought probably water should behave very differently from what it does usually. And indeed, it's very different. So they observe a very high contact angle. They observe also a very small contact angle hysteresis, despite the fact that you have many defects at the solid surface. So you win on two parts. And the reason is the presence of these defects. So these very high contact angles, which, this is something very important of course, cannot be reached just by chemistry. Remember, the maximum value was 120 degrees, and suddenly we gain 55 degrees. Can also be found in nature, in particular in plants. So there was this very famous work by these two German botanists who looked at the different examples that you can find in nature, in particular in plants. 200 plants have the property to be super-hydrophobic. For example, here, the elephant's ear, which is a plant from Indonesia. It's not the ear of an elephant, it's a plant. Here, the magnolia, there again, beautiful textures. Here, the drosera, which is a little carnivorous plant. In each case, you have decoration at the surface, and you have also hydrophobicity. So there is a wax covering all these plants. And so when you come with a liquid on that, this liquid will make a very high contact angle, a very small contact angle hysteresis. These two properties are equally important, and as a consequence, it will run down any slope. And this is the origin of the so-called lotus effect, the fact that if your solid has some contaminants on it, and the liquid is coming from here from the left, as it runs down, if it finds these contaminants, which are here grains of pepper, this liquid takes the grain. So it's in a sense a very trivial effect, the fact that when you have an interface, it gains some surface energy by being coated by a solid. So it's a very general effect. And so what is remarkable here is not the fact that the drop takes the little grains of pepper. It's very natural. What is remarkable is the fact that the drop is mobile. Okay? And so if it's mobile, it's very logical that it takes with it the particles. And so people describe that as a kind of self-cleaning effect. It's not exactly self-cleaning, but it means that just the rain is enough to clean very nicely this surface. You have many animals also, and so probably the one which is the most impressive for its surface energy is water strider. You have here a water strider sitting on a pond, and if you look carefully close to the legs, it's very clear that water is repelled close to the legs. And if you look carefully at the leg itself, it's also decorated by a kind of needles at a scale which is very, very small, as you can see, a scale of a few micrometers. In this case, it's very sophisticated design. Very probably, there is not only this property to have these structures, if you want, but they are also inclined, which means that the friction on water should be anisotropic. The fact that it glides very nicely in one way, but it can push also on water, And so the fact that these spikes are inclined probably plays a role. So it's, of course, something very nice. You can add several properties at the same time when you have these kind of structures. And so, as my colleague John Bush showed, these animals can do many things on water. They are jumping in particular, and so they are incredibly water repellent because you see they never disappear below the surface, which would be a disaster. If you press on the water strider below the surface, it sinks. Okay, it's denser than water. So for it, it's really a matter of life to produce efficient water repellency at the lake. So you have all these nice natural structures, and so of course the question is what is the best one? Can we mimic that, and so on? So these are big questions. And another question, which is maybe simpler, is can we do these structures much simpler? And the answer is yes. You can elaborate structures which are just little pillars, very regular. And this is very convenient for studying the phenomena, because here you can vary independently the three parameters of these surfaces, which are the distance between pillars, the height of the pillars, and the radius of the pillars. And so you can generate families of pillars and then compare the behavior of water as it comes in contact with these surfaces. So here it's very clear that it gives a beautiful pearl, and the reason is that these pillars, exactly like in the previous examples, are hydrophobic. There is a kind of wax which coats everything, and so it's the fact that you have both hydrophobicity, chemical hydrophobicity, plus a structure which generates enhancement of this hydrophobicity and giving this super hydrophobic behavior. And so two possibilities again, either the drop goes inside the pillars or it stands at the top of the pillars, and very naively we could think that this might be preferred generally because these pillars are hydrophobic, and so why should the liquid follow the accidents of a solid that it does not like? This is a bit naive because, of course, when we are in this state, we have many interfaces between liquid and vapor, and each of these interfaces carry a little energy, liquid vapor. And so the comparison between these two states is something interesting, and it tells you that, well, of course, the answer, the most favorable state, depends, for example, on the number of pillars and also on the size of the pillars and so on. And so it tells you that the design can be chosen in such a way that this situation is favored instead of this one. But the reality is slightly more subtle, as we'll see in a few seconds. So this is an experiment where you vary the parameter f, which is the fraction of solid occupied by the pillars. Okay, so if you have 100% of pillars, it means that the surface is flat. You deposit a drop of water, and you observe a contact angle which is slightly obtuse. Okay? If you have 10% of pillars, very obviously the contact angle increased, but you cannot see the origin of the phenomenon. If you have 1% of pillars, the contact angle is still higher, but now you clearly see the origin of the phenomenon because you realized a Leidenfrost experiment. Remember, you put the candle behind and you see the light passing below, and here we see the light passing below, which means that this drop sits at the top of the bed of micronails. So this is the reason why we like to call this state the fakir state, because this drop is a little bit like a little fakir, which is supposed to be on the bed of nails. And so when we see this picture, we immediately guess that indeed it should be very hydrophobic, because below this drop there is 1% of pillars, but there is also 99% of air, and so we are very close to have a solid which is vapor-like. And remember what we said at the beginning, if we are able to make a solid vapor-like, we should reach the ultimate value of 180 degrees. But of course we cannot reach this value because there is still a residual proportion of pillars. And so exactly as we discussed with the fried egg experiment, here the contact angle that you observed is a kind of average between the contact angle on air, which is 180 degrees, and contact angle on the solid, which is maybe 100, weight weighted by the proportion of solid and air below, which is a parameter f. And so you can calculate all of that. Now it's too late to enter these details. There is one case that I like a lot, which is a case when you make the pillars mobile. So for the moment, the pillars are fixed on your solid. And so to make pillars mobile, you take a powder, and it's a hydrophobic powder. So typical size of each grain, it's, let's say, 20, 30 micrometers, same size as the pillars. And you try to mix water with this powder. It seems stupid because the powder is hydrophobic. And indeed, it does not work. When water is coming, the powder does not mix. But, of course, it coats your liquid. Remember what I said. It's always favorable to coat a liquid. And so then, since it's coated, whatever the substrate below, it will not wet this substrate. And then, because you have this kind of protective skin on your solid, they will not coalesce with each other. And so you make a liquid which is decorated by a solid. So now the texture, instead of being on the solid, is on the liquid. But the result is even better. You have something which is purely non-wettable, whatever the substrate. You can take these marbles and put them here on the carpet or on the table, or even on water. They remain globular drops. And so this is a trick, another trick to achieve very high degrees of repellency. So these are pictures of these little marbles. So coming back to the solid case, which is by far the most important, of course you are tempted to make this quantity even smaller, but you guess it will fail. You guess that your fakir state becomes more and more fragile. And indeed, if you keep this proportion constant, about 1%, and if you deposit the drop by two ways which are slightly different, a gentle way here, where very carefully you deposit your drop, or a more natural one, where you throw the drop, you observe that the same drop on the same solid can have different states. And so you come back after 10 minutes, the drops evaporated a little bit, and so you see that in the first case, very nicely, you still see the line of light below, so you are still in the fakir state, very high contact angle, even if you wait, so even if you look at the delta theta quantity, if you want. While here, it's a disaster, because you observe a contact angle which apparently is hydrophilic, despite the fact that it's a hydrophobic surface. So it means that here, as you could guess, the liquid is inside the texture, and because it is inside the texture, it interacts very strongly with the texture, and so it pins very, very efficiently. And so, as a consequence, this state is extremely sticky, while this one, as you can guess, will be extremely slippery. But the question is that they can coexist, and so you have to define how to make this one very robust, how to prevent this transition from taking place. And so people have discussed a lot this question. So how can you trigger, for example, the transition between the two states? And there is one way which is quite funny because it's not completely intuitive, I would say, which consists of varying the size of the fakir. So you start from a given fakir and you make it lighter and lighter. And the trick is very easy. You just let evaporation act. And as a function of time, the film is nearly in real time because the drop is already very small, so evaporation is very fast. And so this is your fakir, which is decreasing in size. And look, it's very, very quick at some point. Here it is. You see, there is a sudden transition. And after you observe this transition, then it becomes extremely flat because once it is inside, it pins very efficiently. So it means, of course, that gravity has nothing to do. The light fakir tends to impale while the big fakir remains at the top. But it tells also that the reason why the little one impales might be related to the fact that the curvature of the drop increases as a function of time because it's evaporating. And so as a consequence, you can find the bottom. And so, of course, this is always the case in this question of metastability. In many cases, the fakir state is only metastable. I told you there are many little pockets of air. So there are many interfaces between liquid and vapor. They hold some energy. And so they are very energetic. But the drop does not know that there is a solid below, and so it can remain at the top. And you have a nucleation barrier, and the question is how can you activate this, can you decrease or increase this nucleation barrier? So it's something that you can study with this little experiment. When you look after evaporation, you find it's a bit vague, but you see clearly that on this surface where the posts were extremely small, so it was a very fragile surface indeed, you find a trace which is a coffee stain effect, and it tells you that the liquid went inside. And of course, if you think of the argument I said, you are tempted to say, well, the air pockets below are curved because the curvature of the drop itself exists, and the curvature must be constant because the Laplace pressure must be constant. And as a consequence, as time is going on, the quantity delta should increase as a function of time. And so at some point, delta should be of the order of h, the size of the pillar. And if it occurs, then there is a contact. And if there is a contact, this contact might propagate if the situation is only metastable. And this transition was studied dynamically by Detlef Lose here and his group. And they made this wonderful movie where you follow what they call the zipping dynamics of the contact as it propagates. So it's a very, very high-speed movie. The typical time scale for the whole process is less than 1 millisecond, and there are only a few pictures where you see the nucleation of this contact and the propagation of this contact, and they could characterize the dynamics of this transition. But what I want to discuss here is something, in a sense, much simpler, which is how to prevent this transition. And so you have two possibilities with the arguments I said previously. One is very naive. It is to say, well, I keep everything constant. In particular, I keep the pillars far from each other so that below the drop there is a lot of air. But now I make these pillars very long. And so it should be difficult for the liquid to find the bottom in this case. So this is a first experiment that you can do. So very long pillars instead of very small ones. Same drop. And you look at the evaporation of this drop. And so you remember there was a critical size below which it was impaling, about this one, but here nothing happens. And so until the end, so maybe at the very end something is occurring, it's not clear. And so you take a picture after evaporation, the coffee stain effect. It should tell you something about where the drop was at the end of its life. And you find something really wonderful, which is the fact that the dust is concentrated on a few pillars and remains close to the top of the pillars. So it means that in this experiment, indeed, the drop never impaled. So there is here a very natural answer to the question, how can you make this Fakir state much more robust? It's very naturally to make the pillars very long. And so this is, I think, the solution which is employed by many animals in particular. When you look at the distance between the leg and the reflection of the leg in water, you see that this distance is very, very large. It's a fraction of a millimeter. And so it means that the pillars, which are little hairs, are extremely long in this case. And as you could see from these animals when they are jumping and so on, it's really crucial that they avoid this pinning transition. The second solution to this question of robustness of hydrophobicity is new, and we don't really know if it's valid, but I think it's very, very nice to know it. It's an experiment which was done only 3 years ago by Lei Zhang in Beijing, and he became interested in the eye of the mosquito. And he had the following idea. He said mosquitoes are living more or less in clouds, so they are probably hit by many little drops, and which I must say I did not know that, but they find us with the eyes. Okay, they are sensitive to the infrared, and so you are in a dark room, you close the light, and we all know that after a few minutes you hear zzz like this close to your. And the reason is very clear. It's that for the mosquito, he sees something pink. It's you, okay, and he gets closer and closer, and he sees regions which are even more red, which are the region where the blood is, and this is the reason why they are close to your ears. And so they are sensitive to the infrared, and so they need the eyes. And so the heat drops, and so of course they must avoid the question of, let's say, condensation or sticking of these drops, despite the fact that these drops are extremely small. And remember, the small drops are more attracted towards the surface than the big ones. Well, it turns out that I think he discovered that the eye of the mosquito is covered by pillars, so very close to the artificial pillars I showed previously, except that the bar, which is here, is 100 nanometers. So they are extremely small compared to the artificial ones, which are 10 micrometers or 1 micrometer. It's 10 times smaller. There is an obvious reason, of course. This surface must be somehow transparent. The light must not be stopped by the presence of roughness. And so you must have a scale, which is here, which is much smaller than the wavelength of light, but also, probably, this is the idea of Lei Zhang, you avoid sticking of the drops, because if the drop is coming here, if it had to find the bottom, which is a disaster, the way to transform a slippery drop in a sticky one, it would have to deform at a scale of 100 nanometers, which implies very, very large curvature, and so very, very large Laplace pressure. And so it's not favorable. This is the proposal of Lei Zhang. So there is no real proof of that, but a very entertaining experiment. I hope you will like it. I like it because I hate mosquitoes, and so I'm very happy of this experiment, where you take a mosquito and you put this mosquito in a freezer, okay, minus 25 degrees. Okay? So after, let's say, half an hour, the mosquito is obviously dead, is extremely cold, minus 25 degrees, and you take it and you put it in a hot, humid chamber. And of course, water condenses on the mosquito, which is so cold, and you take a picture. This is the experiment. And the picture is very impressive. So you have this mosquito with a lot of water on it, and the eyes are completely dry. So it's not, of course, a proof that you have here the first dry anti-fogging surface ever, but it's an interesting sign, and I think there is a beautiful program of research here, which is to try to establish now what's happening as water condenses on this cold animal. There are many examples, of course, of humid anti-fogging surfaces. Our eyes are humid. There is always a film of water, which means that when we cross a cloud, all the little drops of water can go in our eyes and just spread on the liquid, which is water already. And so the natural recipe is to have a wet surface. But, of course, the eye of the mosquito is less sophisticated. It has no possibility of imposing a wet film. And so the trick might be different. So, speaking of this possibility of metastable state, people try to go one step further and to invent omniphobic surfaces. So surfaces which are not repelling only water, but let's say oil as well. So the difficulty with oil is the fact that if you take a flat surface and you deposit your oil, the natural contact angle is not larger than 90 degrees. So we saw that starting from 90 degrees and having a texture, you go at a value which is larger than 90 degrees. We also saw that starting from below 90 degrees and adding a texture, you go below 90 degrees. And so it's not obvious that if you take oil and you put that on a surface, you can reach very high contact angle. However, there are a few groups, and probably the most popular study was the one by Tuteja and collaborators in MIT 3 years ago, where they took a drop of decane, I think, or octane, I don't remember, but a light alkane, and they put it on a solid, and they observe this unprecedented high contact angle. And when you see that, there is only one possibility. There is air trapped below. This is the only possibility. And the design of this particular solid, which of course at the scale of the drop looks flat, is not flat at all. It's decorated with little kinds of mushrooms. So you see there is a foot and there is a hat, and the liquid is coming on that, And it's a very nice trick. Remember the possibility of pinning your line. You have this solid. You have the little mushrooms like this. And this is the next one. And the liquid is coming. It could not stop here, because if it stopped here, you would have a contact angle which is more than 90 degrees, and it's not the case. It's oil on this solid, so we know that the genuine chemical contact angle is smaller than 90 degrees. In this case, it's 40, I think. But as I explore gradually the hat of the mushroom, I find a position here where I can stop. Why? Because if I make a zoom on this, it's something like that. It's an overhang. And so there is certainly one particular position, and only one, where I make the contact angle of, let's say, 40 degrees, which is required to have some equilibrium of my contact line. So here, equilibrium has a very precise sense, which is mechanical equilibrium. If it is achieved, the forces balance, as I showed, and so the line can stop. Okay? And so it can stop at a position such that there is air below. And so the contact angle that you observe is a kind of average between contact angle on air, which is 180, and contact angle on this solid, which is theta smaller than 90 degrees. And so if you make the quantity of air large enough, you can generate very high contact angles. But of course, this is highly metastable, because there is another possibility for the oil, which is to come here, and the surface energy of this second situation is much smaller. And so this is, of course, the practical limitation of that. If you shake a little bit, it will find the bottom. And so the question of robustness of the metastability, which I addressed a little bit previously, is absolutely crucial here. And it's not really solved today. This is an example which I like a lot, because in many cases, people try to make us believe that we find solutions in nature, and we servicely copy these solutions, and we sell them by saying, well, nature invented that, and so we copied, and so we are nearly as good as nature. So this is one case where nature somehow imitated man, because 3 years after that, my friend Neinwis in Dresden found a similar case in nature in a very particular animal, which is called Colombola. So this is Colombola. The size there is a few millimeters, and it's maybe the most common animal at the surface of the Earth. Okay, when you dig in the soil in a forest, you see many of these little animals. People do not know if they are insects or not. The classification is not easy. They are kinds of monsters, and they are living in very humid environment, and also very polluted environment. Polluted in the sense of surfactants, but natural surfactants. Okay? So they must resist water, which must be the case at the very small scale of these animals, of course, because they have little holes, and so if water penetrates, they are dead. Okay? So it's a matter of life. But they must resist to contaminated water. So it's much harder than water strider, which lives on ponds, which is more or less pure water. And so Neinwis had a very brilliant idea. He said they must resist to very special water, and so probably they have a very special texture at the surface. And so he was incredibly patient. So this is a colony of Colombola at the surface of water. They walk and float very easily on water, but they do much better. And he observed very recently that the surface of the body, all the surface of the body, including the legs, I said including the eyes, he said no, they have no eyes, they don't need eyes, they are in the soil, so they have no eyes. And the whole surface is covered by this incredibly sophisticated pattern. And what took more than 1 year of work was to cut one of these. And he succeeded, and he found that the cut of one of these is this incredibly sophisticated texture, which presents many overhangs. Okay? So it seems that it's a kind of elaborated version of that. Okay, so this is one case where nature imitated man. So, do you have questions?
Can you write down the name of that insect?
Colombola. It's not an insect, I was told, but this animal, yeah, this creature. Colombola. So I would like to finish with the fact that when you are in this fakir situation, you have put between the liquid and the solid a certain proportion of air. Okay, and this proportion, of course, the higher this proportion, the more mobile your liquid. And it's something that you can tune, because you can tune the density of defects or structures that you put at the solid surface. And so I would like to finish by showing that this generates very, very special dynamics. So the first series of experiments were about slip. And I said a few words about slip, but I should add something. The fact that when you have a solid surface and you make a liquid flow on this solid surface, people from the beginning of hydrodynamics have to make precise what was the boundary condition at the solid-liquid interface. And you probably know that Navier, in 1840, I think, said that there is, it's not exactly what he said, but you can say that it's nearly that. He said that there is no slip at the solid-liquid interface. So it means that if you have a flow of liquid here, you might have a profile of this flow inside the liquid, and you should have one, because at the solid, if the solid is fixed, there is no velocity. So this is a no-slip boundary condition. And it's a kind of dogma. It's a proposal by Navier, and people then made many calculations about hydrodynamics, and it explains so many things that people have been very happy for, I would say that for 150 years with this boundary condition. And then, well, people try to think about small sizes, microchannels and things like that. And so it became critical to know if indeed there was a no-slip condition. And it was very challenging to prove that maybe in some cases it could be different, in which case you would suppress or minimize the gradients of velocity, which are the source of dissipation. So imagine that there is, a contrario, a very large slip. And so you could imagine, with a very large slip, that the flow is like this. And such a flow does not need any viscous force, or does not imply any viscous force, so it means that you do not need a lot of energy to create a flow like this. So there were many discussions, and in particular it was a kind of battle between different techniques of measurement, and I think that things became more or less clarified only recently, I would say 5 years ago, something like that, in particular by the work of a remarkable researcher in Lyon, in France, Elisabeth Charlet. She discovered many artifacts in the literature. She discovered, for example, that for a given system, you could have 4 orders of magnitude of the measurement of the slip length. I mentioned the fact that between these two situations, there is one which is more reasonable, which is one where you have a gradient of velocity, but you still have possibly a slip at the surface. And the way to quantify this slip consists of measuring this length. And she found that you had 4 orders of magnitude between the slip of it was dodecane, I think, on mica, depending if it were measured in Denmark or in North Carolina or in South Australia. And so she clarified more or less everything, and the result is very simple. If the liquid is hydrophilic, or if the solid is hydrophilic, lambda and flat, lambda is typically at most 1 nanometer. So it's a molecular scale. So it means that any supramolecular flow, you can ignore the slip effect. If the solid is hydrophobic, then lambda is slightly larger. It can become 10 nanometers. It's supramolecular now, but there is no application, I think, to have in mind if you have such a small slip length. It means that a channel whose size would be 10 nanometers. So it could be a channel in cells, for example. I mean, it can exist, of course, but in microfluidics, channels are micrometric. So for large-scale, low-tech applications, these lambda remain extremely small, and so the Navier condition, of course, apply very nicely, which is a very obvious result in a sense, because we have been known for years and years that it works very nicely. But now we are in a very different situation. We have this fakir situation where the liquid flows not exactly on a solid, but on a mixture of solid and air. And so we might think that maybe we generate very large slip. And so the debate was reactivated, and a man who immediately found very interesting result is Jonathan Rothstein in Amherst University. He wrote a very nice review article last year about that, and he did very beautiful experiments where, for example, you measure a flow, and this is a flow profile between two plates. So it's a very classical Poiseuille experiment. The top plate is flat. The bottom plate is textured and hydrophobic. And so if it's hydrophobic, which is the case for these two samples and not for this one, you see that instead of having a Poiseuille flow with a zero velocity at this solid, you can measure a slip velocity at the boundary between your solid, which is not exactly a solid because there is air below. So this result is, I would say, quite natural, but it's very quantitative. And so the nice thing about it is that these people could measure this slip velocity, or equivalently the slip length, for different design of the surface. And they find that this length can be incredibly large. And there is a very nice little argument for understanding that. So I think it will be maybe my last little calculation if I find, where is my eraser? Yeah?
I have a question about these velocity profiles. So in principle, if you look at the red one, so for the hydrophilic case, or the no-slip case, you can see that it more or less is a sort of straight line, and it clearly goes to lambda 0. But if you look at the purple one and the blue one, you can see that there is some kind of sort of kink here.
Yeah.
Lambda goes to infinity.
This.
Yeah, so it goes like.
Yeah. Yeah. So I don't know if the resolution is good enough to argue that there is a kink. You see, it could be also a straight line. Yeah. So there is a very nice little argument to understand that indeed you can generate much larger slips, and that you can even tune these slips by choosing a design. And so here is the argument. So you have a solid, and of course I choose the simplest one, which is this one decorated with little post. We are in the fakir state, so the liquid is coming and it stops here. And now we add a flow. And so this liquid is flowing like this at a velocity, at a mean velocity, which is v. So I am interested in the slip length. And so as you can see from this little construction, if the typical velocity of the flow is v, I know that the gradient which is there is v over lambda. This is the definition of lambda. And this is the force per unit area if I multiply the gradient by the viscosity of the liquid. So this is, in a sense, the definition of the viscosity. The viscous force per unit area is the coefficient of viscosity times the gradient of velocity. And here, the gradient of velocity, if I have a slip length lambda, is the typical velocity divided by lambda. But here, I can also evaluate what is this, yeah?
The velocity profile in the slip length range is linear or parametric?
Yeah, it's linear. It's just the extrapolation. It's the linear extrapolation. Here it's parabolic. And then you take the slope here, and it's linear. Okay? Which explains why it's just V over lambda. So in this case, you can also calculate or evaluate, not a calculation, it's a really scaling law, but you can evaluate what is the typical force you need to drive your liquid. Because you have here a certain distance L between pillars, which is a parameter that you can tune. Your liquid is flowing, and as you can guess, generally, the force, the viscous force necessary to move the liquid above the air is negligible, because the viscosity of air is negligible compared to the viscosity of liquid. If it's water, there is a factor 100. If it's oil, it's even more than that. So it means that the only place where there is viscosity is at the vicinity of the top of the pillars, because here your liquid is flowing on a solid. So what is this typical force? Well, you have here a size which is B, the size of the pillar, and so the typical force should be Stokes force, which is viscosity times V times B. There is a coefficient here, but I ignore the coefficient. And this force per unit length, since you have one pillar per L square, is eta VB over L square. And so now, if you consider the whole flow, you multiply by the number of pillars, but you divide by the same number of pillars here, and so this is the force per unit area which is necessary to drive your liquid. And so immediately when you look at these two expressions, you find that you know what is the slip length in this situation. The slip length is L square over B. So it's a very nice result because it tells you that you can decide what is this slip length, and you can decide that it can be extremely large. Remember the orders of magnitude here. It was 1 nanometer for hydrophilic case, 10 nanometer for hydrophobic case. But now L can be 10 micrometers, B can be 1 micrometer, so L over B can be 10. 10 times 10 micrometers, it's 100 micrometers. So there is a factor which is 10 to the fourth. Okay, so 10,000 times larger than it used to be. So it's really a different world. We are suddenly somewhere else. And there was a huge competition for determining lambda as large as possible. And I think for the moment, the winner of the competition is Kim in UCLA, who measured recently slip lengths of 100 micrometers, exactly the ones we could predict by this naive argument. So before that, the same group in Lyon made interesting experiments of measurement of lambda. So these lambda are much more modest, about 1 micrometer. But 1 micrometer is already extremely large compared to these values. And what is nice in this experiment is that they did twice the same experiment. First, they measured the slip length by moving liquid on a textured surface. And the second experiment was, prior to doing that, they push a little bit on the solid. So they force the liquid to go inside the pillars, and then they push only. And you see that in one case, they are in the fakir state, so they measure lambda values, which are quite large. In the second case, they are in the impaled regime, and of course, they kill completely the slip in this case. So slip is really something very exciting, and I would say that the research today is first to try to find very large slip lengths. This is one thing. And the second question, which is raised in particular by Jonathan Rothstein, is to say, well, is there some macroscopic consequence of that? So for the moment, people think that they can reduce the pressure needed to make a flow in a microchannel of, let's say, 10 micrometers. But maybe, even at the scale of a boat or at the scale of a fish, the way the viscous boundary limit acts with a slip might be different, so that the consequences might be even more dramatic, which is the belief, I would say, of Rothstein. So it's a very interesting question, the way it's related, for example, to the appearance of turbulence or things like that. So the second special dynamics I would like to show you is the fact that now if I go to a viscous limit, so it's not water anymore, I take a viscous, let's say glycerol or honey or anything like that, I put this honey on a solid, I tilt it and I look at the motion. There is quite a remarkable result which was proposed by Mahadevan and Pomo, which is the fact that these drops, instead of sliding, as they do usually, should roll. So they should behave as solids. Okay? And the reason is that because it's very viscous, you expect a small Reynolds number, and at a small Reynolds number, the system chooses, so to say, the way of moving which minimizes its viscous dissipation. And rolling, there is no real viscous dissipation because it's a solid-like motion. And this is completely true, and it has an amazing consequence, which you are going to see here, which is a top view of two drops in a non-wetting situation. They are viscous. You tilt the plate by, let's say, 10 degrees, so they will fall down. There are some traces on each of them, and so you should be sensitive to the fact that it's a pure rolling motion. It's a solid-like motion, but there is another thing, which is, I think, quite amusing, which is the fact that it's a top view, but the small one is quicker. Okay? And this is, of course, very unusual, because when you are in a viscous regime, the Stokes law tells you that the small one is always much, much slower. Okay? The driving force is gravity, r to the cube. Stokes force is v times r, and so v is r to the square. And so if you divide the size by a factor 10, you divide the velocity by a factor 100. And here, if you divide the size by a factor 2, you multiply the velocity by a factor 2. Okay? And the reason is very funny. It's the fact that these drops are, so I will be only very qualitative. So these drops are not exactly spheres. There is a very small deviation from the sphere, which is related that they have a little weight. And so there is a kind of foot here. And so the only place where viscosity enters, because it's a rotation, is close to this foot. And so if you take a drop which is smaller, the foot is much smaller, and so as a consequence, the viscous force is much, much smaller. And it's so small that it becomes the viscous force varies as the fourth power of the size of the drop, while the driving force varies as the third power. And because you have here the velocity, you are able to generate a regime where the smaller the drop, the faster it is. And so this is very surprising, because it tells you that these drops are not only going very quick, they are going all the quicker since they are small, which is very bizarre, because in principle, when you have a viscous liquid, it becomes extremely difficult to move it at a small scale, precisely, because the smaller the scale, the larger the viscous forces. And here it's the contrary. So this word of special dynamics is indeed very special, because it generates a behavior which are, I think, quite unusual. And my very last example will be about this special dynamics on what I like to call the dynamical Leidenfrost effect, which for me is also a very exciting domain. So we saw that a film of air is something very nice. It increases a lot the mobility, changes the laws, and so on. And of course, this film of vapor exists in the Leidenfrost situation. This is a plate which is very hot, and if you come with water on this plate, well, this water is extremely mobile, because all these drops sit on a cushion of vapor. Okay? And because there is no contact, there is no friction, or very, very small friction compared to usually. Typical velocities are 1,000 times larger than the velocities on plastic, for example. So it has nothing to do. But of course, this is very special because you need heat. You need a very high temperature. And so the question is, could you generate film of air by a different way, and in particular using some dynamics? And I would like to show you a few examples of that. So this is an experiment which became immediately very famous. You have a container with oil, and the viscosity of this oil is typically 100 times the viscosity of water. So it's olive oil, typically. And you put a drop of the same oil on this oil. Okay? And so, of course, you expect that oil will merge with oil. And the typical time scale will be a fraction of a second. And so this is a picture which is taken just when you put the drop of olive oil on olive oil. Okay? But you add something. And of course, at this moment, there is a film of air. And this film of air is very thin. And of course, it will get much thinner after a fraction of a second, so that merging takes place. But the idea of if Quéré was to say, and now if I shake the container, then I should make some movement of the fluid, and this movement of the fluid should entrain air which is around, and maybe in such a way that I feed constantly this film of air which is between oil and oil. And so, of course, you have to be quite careful with the amplitude and frequency at which you vibrate the bath of oil. But when you are careful enough, it can be weeks like that. You know? Once you find the right spot in the phase diagram, it's not a small region, it's a reasonable one. Typical amplitude, a fraction of a millimeter. Typical frequency, 50 hertz. And then forever, it bounces because you feed this film of air. So this is a kind of dynamical Leidenfrost effect, where you prevent the contact between, in this case, a liquid and a liquid. Nobody succeeded at making the same experiment with a liquid and a solid. And it would be a big discovery, of course. Think, I don't know, of a windshield, for example. If you vibrate, it would be enough to prevent the coalescence of drops which are falling. It would be a major discovery. But if Quéré says, I never succeeded with a solid, maybe a membrane, a solid which is flexible, might work. A soap film works, for example, so it's nearly a solid. But it's not completely understood, all of that. And of course, if Quéré then did very beautiful experiments, putting many drops, and they interact with each other, and it's wonderful. So this is the first example. The second one is more trivial, I would say. It's an experiment we did with Jessie Bird, and the idea is to move the solid below. So it's a solid, but you move it, and so you say, well, if I move it quickly, probably a film of air will come in with it, kind of boundary layer. My liquid is coming, and it tries to find the solid, of course, because of its inertia, because of its weight, but constantly there is air which is coming, and so maybe I can feed the interval between the liquid and the solid. So in the first experiment, the plate is going to the left, and the velocity is 10 meters per second. Okay, so it's very quick. And this is a drop of glycerol. So viscosity is 1,000 times the viscosity of water. And so it's a high-speed movie. And so it failed. You see, it's very clear that at some point the glycerol touched the solid, and you could see that indeed it's very quick. So you increase very little the velocity of this plate. So now it's, I think, 10.5 meters per second instead of 10. Same drop of glycerol. And in this case, you see that you induce a levitation. And when you have this levitation, you have a small drift, of course, but at the velocity which is much, much smaller, remember, than the velocity of the plate, because there is a small coupling by the viscosity of the air, which is very small, and so you have this resulting drift. So for the moment, I think that nobody understands the velocity at which it takes place. Nobody understands this shape. Nobody understands the drift velocity. There are many, many things to do on this experiment. How it couples with the viscosity of the liquid and so on. The third and last example I would like to show you is just really for imagination, because there are people who try things which should not work, I would say. This is something I would have never bet on that. So it's an experiment by Paul Netzel in Georgia Tech. And he did the following experiment where you have oil. So oil wets everything. Okay, it's a silicon oil. And this oil is on a solid, as you can see, and it does not seem to wet this solid, which is very bizarre. It's shining, and the reason why it's shining is that there is a laser which is coming, a laser beam. And so because of this laser, the drop is heated a little bit. So I was told by Netzel that the difference of temperature between the drop and the plate might be about 30 degrees. So the plate is 20 degrees, the drop is 50 degrees. So it's not a very large difference of temperature. Okay? And so when you heat a little bit this drop, it, as it's obvious from this movie, it does not coalesce. It's vaguely moving because there is some movement in the atmosphere, and it's enough to move it because there is no friction, but it does not coalesce. So what is the mechanism here? It's not really clear, but it might be the following thing. So you have, according to Netzel at least, so T minus here, T plus here, but this point is close to the solid, so this point is T minus. And so the temperature in the drop is not homogeneous. And because the solid is very large, the T minus temperature is maintained, and because you keep the laser on, the T plus is maintained. So you always have this difference of temperature. Because the temperature is not homogeneous, the surface tension is not homogeneous. Where the temperature is high, the surface tension is low, gamma minus, gamma plus. And so you have a flow from the region of low surface energy to the region of high surface energy inside the drop. And this flow takes air with it above. And so air is brought at the right place, at the place where we precisely want to see air, which is between the liquid and the vapor. And so this is a very subtle mechanism which is proposed to explain this experiment. And of course, in this experiment, it's completely symmetric. And so there is no movement, of course, of the drop. But now, if you shift a little bit the laser, you would expect one of these arrows to be larger than the other one. And so you might create some asymmetry between the two arrows, which means that you might create some movement. And so it's not only a question of making a drop levitate, but you can also manipulate this drop. And so this is this very last experiment where the drop is moving because the laser is moving. And so as a consequence, you generate a little force which makes the liquid follow the light, something like that. And with this beautiful experiment, I thank you for your attention.
What's absorbing a laser in the liquid?
What's
I guess I would expect light to just pass through and not very much.
Yeah, so I don't remember if he has particles inside the liquid, for example, to absorb the light. Yeah, this is something I don't. It's a shame because there was a referee of this paper, and I remember exactly asking this question. So there was an answer, and I think that he put some little particles inside, but I'm not completely sure of that.
And the temperature, I guess there's something might absorb.
Mm-hmm. Yeah, of course. Yeah, because you need to create this difference of temperature. Yeah.
On the omniphobic surface, I didn't get the length scale for the non-insect surface structure.
Non-insect? This one? Oh, the non-insect. Okay, it's Colombola. Yeah, I see what you mean. The length scale, was it? So I think this is 200 nanometers, if I remember correctly. Okay.
Would that then be small enough to keep, let's say, natural surfactants, so to keep, like my cells out? Or
No, it's not small enough. No. no. There is no steric effect of this kind. No. It remains largely supramolecular, and of course, micelles are also supramolecular, but no. The scale is larger. Yeah. It's you see. These bumps are a few micrometers, and then each of them is decorated by this sub-micrometric scale, but it's not visible here, but this is 200 nanometers. And so, 200 nanometers, this is not so far from being, but the micelle is 5 nanometers, you see, so it's really much, much smaller. And he tried actually to, it's a difficult experiment, to place drops with surfactant on the carapace of these bugs, and they repel everything. They repel everything. He tried. They do not repel silicon oil, but there is no silicon oil in the soil generally, so it's okay.
Yes. About the slip length, you said that it's like correlated with L squared divided by B, but that will imply that if you are getting your L to infinity and your B infinity small, then you are having you will not have any textures left. So somewhere it should be an equilibrium, I think.
Yeah, you say that if L becomes large or B small, this length diverges. And indeed, many properties become apparently very spectacular when we are in this limit, where we have very few, very thin pillars. But this limit is not, is more than fragile. It cannot sustain anymore the liquid. So your question is very interesting, is to say, obviously, we are tempted to make L large and B small to have a big lambda. But at the same time, we know that L large and B small make the system collapse, where we completely lose the property lambda. And so it's exactly the same kind of debate as we had for the contact angle, where pillars far from each other and which are very thin makes a very small fraction of solid below the liquid. But there again, there is a kind of compromise. And so today I would say that really people are here. How to make this quantity large and the state, the Fakir state, robust enough to have nice experiments and to have, for example, when you push liquids in channels, you need pressure. So it means that you push on your liquid, and so if you push on your liquid, there is a risk that your liquid is invading the structures. And so, so it's really the question for the design which has to be given to the surfaces.
Anybody tried experiments in which the patterning changes gradually to direct?
I hesitated to include something like that. There are few experiments of this kind, and the hope that we had when we did this experiment was that if the density, for example, is changing as a function of space, then the hydrophobicity should change, and so you should have spontaneous displacement along the texture. In particular, in this case, you should go to regions which are less and less dense, more and more dense in pillars, because you start from very hydrophobic regions for your liquid, and it goes to regions which are less hydrophobic. I don't know anybody who succeeded in doing that. When we did this experiment, we did not observe anything, and then we shake a little bit, and then it was moving. But there is some pinning also, and so the forces that you generate are a bit weak, and so generally they are opposed by the pinning which takes place at the top of the pillars. And so it would be very nice to do the same experiment with round pillars on which pinning is, like these ones. Yeah, exactly. Yeah, this would be wonderful. Yeah, and so it's not so easy to make, but it's feasible. And of course, spontaneous displacement of liquid at a solid surface is something very interesting, because it means that, for example, if you imagine a condenser, you condense your vapor, but it's everywhere, and if at the same time you have a drift, it's very nice because you concentrate what you are doing, and so it's a very beautiful achievement. Yeah.
in the last experiment where there was demonstrated movement of the particle on the surface, isn't that just optical tweezers effect? Because they do the same thing, right?
I have to think about. There is no in the paper by Neitzel. There is no explanation actually. It's a fact. So I think it's not really explained. I was tempted to say that if you, but I just imagined that for tonight. I mean, I never thought deeply about that. So I'm quite confident that the reason for levitation is correct, but for the displacement, I'm less firm. Yeah, you might be right. In particular, there is something which is absolutely correct, which is the fact that once you make a liquid levitate, the force that you need to displace it is incredibly small. It's of the order of micronewton, let's say. So it's of the order of the weight of the drop divided by a factor 100, 1000, which is very far from being what we know. For a drop on a window pane, the force to displace it is larger than the weight because it remains stuck. Okay, so here we are in a completely different. So any little force might explain the displacement.
Also, I think for optical trapping you need a focused laser, and it looked to me like the laser there was collimated. So I'm not sure if, I don't know, because it seemed like only the top half was illuminated, the bottom half wasn't. But maybe you can also make optical trapping in a collimated laser beam that's going perpendicular to the direction of gravity, but
you can collimate light in this in the beam size of this little droplet.
The size of the beam here is comparable to the size of the drop. Yeah, indeed. Yeah. I don't know, of course, also what are the reflection properties of the bottom. All of that might matter.
Then if the drop moves and the laser beam is focused, the laser beam has to move.
Yeah, here the beam was moving. Yeah. And the drop was following the beam. Yeah.
The movie you have shown where you drop over the hot plate.
Yeah.
The droplets are moving outside.
Yeah.
Is there any particular reason for that? It's just the inside.
They are moving everywhere, and so I should just say that they don't need. It's exactly what I said previously. They don't need a big force to move in a given direction, and so there is something random in the way they bounce on this solid, which fixes in an arbitrary way the direction they take. In this particular case, the plate was very flat, and so there was no privileged direction, and so they split in. Yeah, it's an interesting question. We might do the statistics of that and to. Evaporation is very slow. It's paradoxical because it's a very hot surface, but because you have this film of vapor which is quite thick and which is a very good insulator, a drop of water of 1 millimeter on a plate which is 300 degrees has a lifetime which is 2 minutes. It's a huge time. And Leidenfrost, very long ago, observed already that, and he understood that it was related to the fact that there was no contact. For example, if you deposit a drop of water on a solid at 100 degrees, the lifetime is 1/10 of a second. Okay? If you increase the temperature of the plate by 200 degrees, this lifetime, as I said, is multiplied by a factor 1000. You see? There is a kind of divergence of the lifetime because of the film of vapor. So at the scale of the movie, where it took a fraction of a second, the evaporation is completely negligible. Yeah. It's a good point because we naturally would think that evaporation plays a role, maybe by boosting the drop, you see, or rocket effect or something like that. I think it's not the case. Okay, time to conclude, I think. So thank you.